What if I told you that right now, as you watch this, an invisible army is hiding in the vast emptiness between galaxies? Not ghosts or dark matter, but something far more tangible, yet somehow, we've lost half of it. Meet the missing baryons, the universe's most frustratingly elusive puzzle. These are the particles that make up everything you can see, touch, and even are the building blocks of stars, planets, and every speck of dust in between. But here's the kicker. When scientists tallied up all the baryons that should exist based on the Big Bang's recipe, nearly half of them were gone, vanished. Like a cosmic magic trick played on the grandest scale, for decades, astronomers scratched their heads, searching every corner of the known universe. Galaxies, check. Nebulas, check. Yet the numbers still didn't add up. It's as if the universe handed us a jigsaw puzzle, only to hide half the pieces in plain sight. But recently, something extraordinary happened. Clues began to emerge, hints of an invisible web, a sprawling network of superheated gas threading through the voids between galaxies. This wasn't just empty space, it was a secret highway, buzzing with energy and movement. The missing baryons weren't missing at all. They'd been there all along, hiding in the shadows, whispering their presence through faint glimmers of X-ray light. So why does this matter? Because this isn't just about solving a cosmic accounting error. It's about uncovering the hidden architecture of the universe itself, the scaffolding that shapes galaxies, fuels star formation, and maybe even holds the keys to understanding how everything we see came to be. Imagine standing at the edge of the ocean, knowing there's an entire world beneath the waves you can't see. That's where we are right now with the cosmos. And today, we're diving in. We'll follow the trail of these ghostly particles, explore the mind-bending methods scientists used to find them, and ask the big question: what else is lurking in the darkness, waiting to be discovered? Buckle up, the universe is about to get a lot more interesting. Baryons are the universe's unsung heroes, the tiny, fundamental particles that literally hold everything together. Think of them as the bricks in the cosmic construction site. Every star, every planet, even the screen you're staring at right now is made of baryons. Protons and neutrons, the heavy lifters inside every atom's nucleus, those are baryons. Without them, the universe would be nothing but a sea of lightweight electrons and ghostly neutrinos, drifting through an empty void. But here's where things get weird. When scientists calculated how many baryons should exist based on the afterglow of the Big Bang, that faint microwave whisper we call the cosmic background radiation, they hit a snag. The math was clear. About half of them were nowhere to be found. It's like baking a cake, following the recipe perfectly, only to pull it out of the oven and discover half the batter is just missing. This wasn't some minor rounding error. It was a gaping hole in our understanding of the cosmos. For years, astronomers turned their telescopes to every corner of the sky, hunting for clues. They tallied up baryons in stars, galaxies, and the thin gas floating between them. But no matter how carefully they counted, the numbers fell short. It was as if the universe had a secret stash, squirreled away in some invisible vault. The implications were staggering. If we couldn't account for half the normal matter, the stuff we're literally made of, how could we trust our models of how galaxies form, how stars ignite, or even how life itself came to be? Then came the breakthrough. Researchers realized the missing baryons might not be hiding in some distant, exotic place, but right under our noses, or rather, between everything we could see. The space between galaxies isn't truly empty. It's threaded with a faint, superhot web of gas, so diffuse it's nearly invisible. This intergalactic highway, glowing weakly in X-rays, was the perfect hiding spot. So why did it take so long to find them? Imagine trying to spot a single lit match from 1,000 miles away. That's the challenge astronomers faced. These baryons aren't clumped together like stars or planets. They're spread impossibly thin, a fog so delicate it barely leaves a trace. But with cutting-edge telescopes and clever techniques, scientists finally began piecing together the puzzle. The discovery didn't just solve a cosmic accounting error, it rewrote the map of the universe. Those missing baryons are the glue connecting everything, the hidden currents shaping the cosmos. And if we've overlooked something this fundamental for so long, what else is still out there, waiting to be found? The mystery of the missing baryons begins with one of the most precise calculations in all of cosmology, the cosmic ledger left behind by the Big Bang. When the universe was just a newborn, barely 380,000 years old, it released a snapshot of its contents in the form of the cosmic microwave background. This faint glow, detectable even today, acts like a detailed inventory list. It tells us exactly how much normal matter protons, neutrons, and electrons should exist in the cosmos. The numbers were crystal clear. Baryons should make up about 5% of the universe's total mass and energy. Yet when astronomers added up all the visible matter, stars, galaxies, gas clouds, and dust, they came up shockingly short. Less than half the expected baryons were accounted for. It's like balancing your checkbook, only to find half your savings have vanished without a trace. The immediate suspect, maybe they were hiding in black holes or locked away in some exotic, undetectable form. But black holes turned out to be too few, and exotic matter didn't fit the bill. The real answer was far more subtle and far more clever. The breakthrough came when scientists turned their attention to the vast, seemingly empty expanses between galaxies. We used to think of these regions as cosmic deserts, barren voids where nothing of interest happened. But that assumption was dead wrong. Hidden in those voids is an intricate web of ultra-hot, incredibly thin gas, so diffuse it's nearly invisible. This isn't just any gas. It's ionized plasma, heated to millions of degrees, strung between galaxies like luminous threads in a spider's web. Spotting this gas is like trying to see the steam rising from a cup of coffee in a foggy room. Ordinary telescopes can't detect it because it doesn't emit visible light, but X-ray telescopes, tuned to catch the faint high-energy glow of superheated matter, finally revealed the hidden baryons. They weren't lost, they were hiding in plain sight, woven into the fabric of the universe itself. Why does this matter? Because this intergalactic medium isn't just a cosmic curiosity, it's the backbone of the universe. It channels energy, shapes galaxy formation, and may even hold clues to how the largest structures in the cosmos came to be. Solving this puzzle didn't just fill in a missing piece, it reshaped our understanding of where and how the universe keeps its secrets. And if we've been wrong about something as fundamental as where matter hides, what else have we overlooked? Picture the universe not as a scattering of isolated galaxies, but as a colossal, interconnected neural network, an intricate spiderweb stretching across billions of light years. This is the cosmic web, the hidden skeleton of our universe, where galaxies cluster like glowing beads along twisting threads of dark matter and gas. And right there, in those nearly invisible filaments, lies the answer to the missing baryon mystery. For decades, astronomers suspected these vast, wispy tendrils might hold the key. The cosmic web isn't just empty space between galaxies, it's a dynamic highway of matter, shaped by gravity's relentless pull. Imagine pouring syrup onto a griddle. It doesn't spread evenly. Instead, it forms rivulets and pools drawn together by surface tension. On a cosmic scale, gravity does the same thing, sculpting ordinary matter into a labyrinth of filaments. These threads are so thin, they make a spider's silk look like rope, just a few atoms per cubic meter, yet spanning unimaginable distances. But here's the twist. While dark matter forms the web's framework, the missing baryons hide in the gossamer strands of hot gas draped over it. This gas isn't lukewarm or even warm, it's scorching, heated to millions of degrees by the violent shocks of collapsing matter and the furious energy of ancient cosmic collisions. At those temperatures, it glows faintly in X-rays, a whisper of light against the overwhelming blackness of space. Detecting this faint signal was like trying to hear a single violin in a hurricane. Traditional telescopes couldn't see it, but X-ray observatories like Chandra and XMM-Newton changed the game. By stitching together thousands of observations, astronomers finally mapped the web's ghostly glow, pinpointing where the missing baryons had been lurking all along. Yet the cosmic web isn't just a hiding spot, it's a cosmic conveyor belt. These filaments channel gas into galaxies, fueling star birth and shaping their evolution. Without this hidden network, galaxies might never have formed at all. And if we've only just begun to see this invisible scaffolding, what other secrets might it still be holding? The universe, it seems, is far more connected and far more mysterious than we ever imagined. Deep in the spaces between galaxies, where darkness seems absolute, there's a sea of matter so hot and thin it defies ordinary detection. This is the warm, hot intergalactic medium, or WHIM, a theorized plasma so wispy a single cubic meter of it might contain just a handful of atoms. To put that in perspective, the air we breathe packs in around 25 quintillion molecules in the same space. Yet despite its ghostly tenuousness, the WHIM could hold the key to solving the missing Baryon mystery. What makes this plasma so special? Temperature. The WHIM isn't just warm, it's blisteringly hot, reaching millions of degrees. At these extremes, atoms are torn apart, their electrons stripped away, leaving behind a soup of charged particles. This ionized state makes the WHIM nearly invisible to optical telescopes, which rely on visible light. Instead, it reveals itself through faint X-ray emissions and subtle distortions in the light of distant quasars as their beams pass through these invisible tendrils. Detecting the WHIM is like trying to photograph steam with a camera designed for icebergs. Traditional tools see right through it, but astronomers have developed clever workarounds. One method involves studying absorption lines, the fingerprints left when the WHIM sips specific wavelengths from the light of brilliant quasars billions of light years away. Another exploits the Sunyaev-Zeldovich effect, where the WHIM-hot electrons scatter cosmic microwave background radiation, leaving minuscule temperature ripples we can measure. The real challenge, the WHIM isn't a uniform fog, it's a tangled, ever-shifting network. Some filaments are denser, others more diffuse, and all of them warp and ripple under the influence of dark matter's gravity. Mapping it requires piecing together thousands of observations, like reconstructing a city's skyline from a handful of scattered flashlight beams. Yet every new discovery sharpens the picture. Recent studies suggest the WHIM might not just contain missing baryons, it could actively ferry them across the cosmos, channeling matter into galaxies and fueling the birth of new stars. If so, this elusive plasma isn't just a hiding place for lost matter. It's the universe's silent architect, shaping everything we see from the shadows. And if we're only now learning to see its handiwork, What other invisible forces might be sculpting the cosmos beyond our sight? Finding the WHIM is like trying to track a whisper in a thunderstorm. The signals are achingly faint, buried under cosmic noise. To hunt down these elusive baryons, astronomers had to turn the universe itself into a detective tool. X-ray spectroscopy became one of their sharpest instruments. Picture this: when the WHIM superheated gas floats in front of a distant quasar, those million-degree electrons absorb specific X-ray wavelengths, leaving tiny dips in the quasar's light, like fingerprints in wet ink. Telescopes like Chandra and XMM-Newton painstakingly collect these spectral fingerprints, each one a clue to the density, temperature, and location of the missing matter. But there's a catch. The WHIM signal is so weak that even Chandra, with its eagle-eyed precision, might need weeks of staring at a single patch of sky just to catch a flicker. Then there's ultraviolet spectroscopy, a game-changer for spotting slightly cooler strands of the WHIM. Instruments like the Hubble Space Telescope's Cosmic Origins spectrograph act as cosmic bloodhounds, sniffing out the faint UV glow or absorption lines from oxygen and neon ions. These elements are tracers, the breadcrumbs left behind as the WHIM weaves through space. But here's the kicker: the WHIM is so diffuse that these absorption lines are often thinner than a pencil line drawn across a football field. Teasing them out requires stacking observations from dozens of quasars, stitching together a statistical map from fragments of light, the real innovation. Combining both methods, X-rays reveal the hottest, most energetic filaments, while UV catches the warmer, quieter threads. It's like using night vision and thermal goggles together to spot a camouflaged creature. Sometimes, astronomers even exploit cosmic luck when a galaxy cluster's gravity bends light from a background quasar, creating a natural magnifying glass that amplifies the WHIM whisper-thin signal. Yet the challenges don't end there. Earth's atmosphere blocks X-rays and much of the UV spectrum, forcing us to rely on expensive, fragile satellites. And even in space, the WHIM signal is swamped by foreground noise, like trying to hear a flute in a symphony where every instrument is playing at once. Future telescopes, like ESA's Athena mission, promise sharper eyes and ears, but for now, every detection feels like coaxing secrets from a universe that's determined to stay silent. What's astonishing isn't just that we've found these hidden baryons, it's how creatively we've had to look. The hunt has pushed technology to its limits, turning entire galaxies into backlighting tools and statistical noise into a treasure map. And if we've had to work this hard just to see what was right in front of us all along, what other invisible wonders might still be waiting, just beyond the edge of our perception? Two of the most powerful tools in the hunt for missing baryons aren't even on Earth, they're orbiting high above our atmosphere, where the murky veil of air can't blur their vision. NASA Chandra X-ray Observatory and ESA's XMM-Newton have spent decades staring into the abyss between galaxies, armed with instruments sensitive enough to catch the faintest X-ray whispers of superheated gas. These telescopes don't just take pictures, they dissect light like cosmic, forensic scientists, revealing the fingerprints of elements scattered across the voids. Chandra, launched in 1999, is the precision scalpel of X-ray astronomy. Its ultra-sharp mirrors can resolve details finer than a second of arc, the equivalent of reading a stop sign from 12 miles away. This razor focus let Chandra pinpoint strands of the cosmic web by detecting the telltale glow of oxygen ions heated to millions of degrees. One landmark study trained Chandra on a distant quasar for over 5 million seconds, That's nearly 2 months of continuous observation, and finally spotted the absorption lines of the WHIM, like catching the shadow of a ghost. But Chandra has limits. Its field of view is tiny, covering less than 1% of the area of the full moon in a single snapshot. To map the cosmic web, astronomers must painstakingly stitch together thousands of these narrow glimpses, like assembling a mosaic with postage stamp-sized tiles. And then there's the competition for time. Chandra's observations are so in demand that only 1 in 5 proposals gets approved, leaving vast stretches of the web unexplored. Enter XMM-Newton, Europe's workhorse X-ray telescope. Launched the same year as Chandra, it trades some precision for sheer light-gathering power. Its nested mirrors collect more X-rays than any previous telescope, making it ideal for surveying broad swaths of sky. Where Chandra might spot a single filament, XMM-Newton can reveal the larger tapestry. In 2020, it detected sprawling reservoirs of hot gas around galaxy clusters, proving the WHIM isn't just confined to filaments. It's a pervasive ocean, with currents flowing everywhere. Yet even XMM-Newton struggles with the WHIM elusiveness. The plasma's signal is often drowned out by brighter X-ray sources, like trying to hear a murmur at a rock concert. And both telescopes face a cruel irony. The hotter and more energetic the gas, the easier it is to spot, but the majority of the WHIM might be cooler, lurking just below their detection thresholds. What's next? Missions like ESA's Athena, set to launch in the 2030s, promise revolutionary advances, with resolution 50 times sharper than XMM-Newton and a field of view 20 times wider than Chandra's. It could finally map the cosmic web in high definition. Until then, every flicker of X-ray light these telescopes capture is a breadcrumb leading us deeper into the universe's hidden architecture, one invisible thread at a time. Imagine turning a flashlight on in the darkest room imaginable. The beam cuts through the blackness, illuminating dust particles you never knew were there. In the cosmic sense, quasars are those flashlights, these brilliant, distant objects, supermassive black holes devouring matter at the centers of galaxies, blast out beams of light so intense they outshine entire galaxies. And when that light journeys across the universe, it doesn't travel through empty space. It passes through filaments of the WHIM, the same wispy plasma hiding the missing baryons. Here's the magic. Just as dust scatters a flashlight's beam, the WHIM leaves its mark on quasar light in a way scientists can decode. The key lies in absorption lines, ghostly gaps in the quasar's spectrum, where specific wavelengths of light have been stolen. Every element in the WHIM hot gas leaves a unique fingerprint. Oxygen, stripped of some of its electrons at million-degree temperatures, sips up X-rays at precise energies. Neon does the same, but at slightly different wavelengths. It's like a barcode, where each missing line reveals not just what's there, but how much, how hot, and even how fast it's moving. The finer the lines, the more diffuse the gas. Some are so faint they'd be invisible in a single quasar's spectrum. So astronomers stack observations from dozens, even hundreds, of quasars to tease out the signal from the noise. This technique isn't new. Back in the 1960s, astronomers first noticed odd dips in quasar light and realized they were seeing something profound: intergalactic gas. But today's instruments, like the Hubble Space Telescope's Cosmic Origins spectrograph, have turned those early hints into a precision science. Hubble can detect absorption lines so subtle, they're like spotting a single missing stitch in a tapestry the size of a city. And when combined with X-ray data from Chandra, the picture grows even sharper. Hotter filaments glow faintly in X-rays, while slightly cooler strands betray themselves in ultraviolet. But quasars don't just reveal where the missing baryons are, they show how they're moving. Absorption lines aren't static, they shift slightly based on the gas's velocity. Some filaments are racing toward us, others away, woven into a dynamic web that shudders under the pull of dark matter's gravity. In one groundbreaking study, researchers used quasar light to map a filament stretching tens of millions of light years, its gas flowing like an invisible river into a distant galaxy cluster. The irony: quasars are random cosmic lighthouses, scattered unevenly across the sky. We can't choose where they are. We can only work with the beams nature gives us. That means gaps in the map, whole regions of the cosmic web still shrouded in shadow. But every new quasar studied adds another stitch to the tapestry, another clue to the architecture of the invisible universe. And as telescopes grow more sensitive, those faint absorption lines, once whispers at the edge of hearing, are starting to tell their stories louder and clearer than ever before. To uncover the secrets of the missing baryons, scientists didn't just rely on telescopes, they built entire universes inside supercomputers. Cosmological simulations are like cosmic time machines, letting researchers rewind the history of the universe and fast forward through billions of years of evolution to see where baryons should be hiding. These aren't just simple models, they're staggeringly complex digital realms where trillions of particles interact under the laws of physics, painting a dynamic portrait of how matter weaves itself into the cosmic web. One of the most revealing simulations, the Illustris TNG project, starts with a universe just a fraction of a second old, a hot, dense soup of particles, and lets gravity, gas dynamics, and even star formation play out over eons. The results are mesmerizing. Filaments of gas stretch across the void, knotting into galaxy clusters, while vast bubbles of emptiness form between them. But the real revelation: when scientists tally up the baryons in these simulations, they match the missing amounts almost perfectly. The simulations predict that roughly half the normal matter should be floating in those thin, hot filaments, exactly where the WHIM was later discovered. Yet simulations aren't perfect mirrors of reality. They rely on assumptions about dark matter's behavior, the physics of gas cooling, even the explosive energy of supernova. Early models missed key details, like how supermassive black holes pump energy into their surroundings, heating gas and pushing it farther into intergalactic space. But each discrepancy between simulation and observation has sharpened the science. When telescopes found less cool gas than expected, for example, researchers tweaked their models to account for ultraviolet radiation from young stars, which evaporates gas clouds like morning mist. The gold standard: simulations that predict phenomena before telescopes detect them. In 2018, one model forecast that the WHIM filaments should emit faint, specific X-ray signals. Months later, Chandra spotted precisely those signals in the data. It was a eureka, a moment a simulation had reached into the darkness and pointed to where the missing baryons were hiding. But mysteries remain. Some simulations suggest the WHIM might be clumpier than observations show, or that pockets of ultra-dense gas could be lurking in unexpected places. Others hint at a warm phase of the WHIM, cooler than the million-degree plasma we've detected but still too hot for current telescopes to see. These gaps aren't failures, they're guideposts, showing where to aim the next generation of instruments. The real power of simulations lies in their ability to ask, what if? What if dark energy behaves differently? What if primordial black holes seeded the cosmic web? By playing out these scenarios, simulations don't just help us find missing matter, they reveal how the universe could have worked, narrowing down the infinite possibilities to the one reality we inhabit. And with every iteration, the virtual cosmos grows a little more lifelike, inching us closer to understanding not just where the Baryons are, but how they shape the story of everything. Dark matter and missing baryons might sound like two sides of the same cosmic mystery, but they are fundamentally different puzzles, each with its own set of clues and implications. Let's break it down. Baryons are the ordinary stuff you're made of: protons, neutrons, and electrons. They're the bricks and mortar of visible reality, from the screen in front of you to the farthest visible galaxy. Dark matter, on the other hand, is something else entirely, an invisible, enigmatic substance that doesn't interact with light or ordinary matter except through gravity. We know it's there because its gravitational pull sculpts galaxies and bends spacetime, but we still don't know what it is. Here's where confusion creeps in. When astronomers realized half the universe's baryons were missing, some wondered if dark matter might be hiding them, but that's like mistaking a shadow for a lost wallet. Dark matter isn't missing, it was never part of the baryonic inventory to begin with. Think of it this way: if the universe's matter were a pie, baryons are the 5% slice we can see and taste. Dark matter is the 27% slice that's utterly flavorless and invisible, yet its weight holds the pie together. The missing baryons, they're just a fraction of that 5% slice that somehow slipped off the plate. The hunt for each reveals how differently they hide. Dark matter's ghostly nature means it could be anything from undiscovered particles to primordial black holes, objects that don't emit or absorb light. Missing baryons, though elusive, play by familiar rules. They're still protons and electrons, just scattered so thinly they're nearly invisible. While dark matter's gravity dominates the cosmos, shaping galaxies into vast webs, the missing baryons are more like cosmic fog, clinging to those webs but refusing to glow brightly enough to see. Why does this distinction matter? Because solving one puzzle doesn't unlock the other. Finding the WHIM hidden baryons won't explain dark matter's identity, and discovering dark matter won't account for the lost baryons. They're separate chapters in the same epic, the story of how the universe hides its secrets. And if we've learned anything from this cosmic detective work, it's that the universe is far sneakier than we ever imagined. Galaxies aren't just serene islands of stars, they're cosmic pressure cookers, violently ejecting matter into the void. When massive stars die in supernova explosions, they don't fade quietly. These stellar detonations unleash shockwaves so powerful, they can blow entire rivers of gas clear out of their host galaxies. And it's not just stars, supermassive black holes at galactic centers, feasting on surrounding matter, belch out jets of energy that fling baryons into intergalactic space like cosmic confetti. These phenomena, collectively called galactic winds, might be one of the universe's best-kept secrets for hiding ordinary matter in plain sight. Take the Milky Way's own history. Our galaxy has likely blown away enough gas to build billions more stars, equivalent to hurling entire solar systems worth of material into the darkness between galaxies. For decades, astronomers assumed most of this ejected matter would eventually fall back, pulled home by gravity. But recent simulations reveal a startling truth. Much of it escapes forever, joining that diffuse sea of hot plasma threading the cosmic web. The numbers are staggering. Some galaxies, especially younger ones frenetically forming stars, can eject up to 90% of their baryons this way. It's as if the universe has a hidden recycling program, one that shuttles matter from galaxies to the voids, where it becomes nearly invisible. Black holes take this process to extremes. When quasars ignite, their radiation pressure pushes surrounding gas outward at speeds approaching thousands of kilometers per second, fast enough to cross the distance from Earth to the Moon in under a minute. These outflows don't just carry stray atoms, they drag along heavy elements like oxygen and iron, seeding the intergalactic medium with the building blocks of future worlds. Ironically, the same forces that create galaxies' gravity pulling matter together also tear them apart, scattering their substance across the cosmos. Here's where galactic winds get really clever. The ejected gas doesn't just vanish, it becomes fiendishly hard to detect. As it expands into the near vacuum of intergalactic space, it thins out dramatically, cooling just enough to avoid glowing in X-rays, but staying too hot to form detectable clouds. It's the astrophysical equivalent of a magician's sleight of hand. Matter transformed into a state that slips between the cracks of our observational tools. Yet these winds aren't just destructive. They shape galaxies like cosmic sculptors. By ejecting gas, they regulate star formation, preventing galaxies from burning through their fuel too quickly. Some simulations suggest that without these outflows, galaxies like ours would have exhausted their gas reservoirs billions of years ago, leaving the universe dark and lifeless. So while galactic winds might hide baryons from view, they also play a crucial role in making the cosmos as vibrant and varied as we see it today. The implications ripple outward. If galactic winds are this efficient at redistributing matter, they could explain why early calculations of baryon counts came up short. We weren't accounting for all the material that had been invisibly exiled. And if winds from countless galaxies have been pumping baryons into the cosmic web for billions of years, the WHIM might not just be a passive reservoir. It could be an active player in the universe's grand cycle of matter, a dynamic conveyor belt constantly replenished by the breath of galaxies themselves. That changes everything because it means the missing baryons aren't lost. They're on the move, part of a story far larger than we ever imagined. Galaxies don't just form in isolation, they're sculpted by the invisible rivers of matter flowing through the cosmos. The missing baryons, those elusive particles hiding in the WHIM, aren't just a bookkeeping error. They're a critical piece of the puzzle in understanding how galaxies grow, evolve, and even fade away. Picture a galaxy as a living organism, constantly breathing in and out. It draws in gas from the cosmic web to fuel star birth, while supernova and black holes blast material back out into the void. But if half the baryons are stranded in intergalactic space, that changes the entire equation. Take star formation, for example. Galaxies need a steady supply of cool gas to create new stars. Yet simulations show that without enough baryons falling in from the surrounding filaments, galaxies can starve prematurely. The WHIM ultra-hot gas is too energetic to collapse into stars directly. It's like trying to build a snowman with steam. But here's where it gets fascinating. Gravity and time work their magic. As the cosmic web's filaments slowly funnel gas toward galaxies, shocks and collisions can cool some of it down, condensing it into star-forming fuel. The missing baryons aren't just lost, they're trapped in a cosmic traffic jam, awaiting the right conditions to join the party. This bottleneck might explain why some galaxies fade out earlier than expected. Observations reveal that massive galaxies in the modern universe are often red and dead, packed with aging stars but lacking the blue glow of young, hot ones. One leading theory: they've exhausted their gas reserves because the WHIM baryons never made it back home. In contrast, galaxies nestled in denser regions of the cosmic web, where filaments are richer and more interconnected, tend to stay active longer, like cities fed by abundant trade routes. But the influence goes deeper. The distribution of missing baryons could shape a galaxy's very structure. Spiral arms, those elegant swirls in galaxies like the Milky Way, rely on precise densities of gas to maintain their shape. If too much baryonic matter is locked away in the WHIM, the delicate balance tips. Some models suggest this might explain puffed-up galaxies with faint, diffuse disks. Their missing baryons left them without enough material to form tight, bright spirals. Then there's the role of feedback, the way galaxies self-regulate by expelling gas. Supermassive black holes act like cosmic pressure valves, heating surrounding gas so intensely it escapes into the WHIM. In a sense, galaxies and the missing baryons are locked in a dance. What's pushed out might someday fall back in, recycled by the slow churn of gravity. The problem is, in vast intergalactic voids, someday can mean billions of years, far longer than a galaxy's star-forming prime. This isn't just theoretical. Astronomers have spotted galaxies with bizarrely low baryon counts, their star formation stunted as if gasping for breath. Others, like the spectacular M87, sit at the intersection of cosmic filaments, drawing in enough WHIM-fed gas to power jets of plasma thousands of light-years long. The difference between a galaxy thriving or withering might come down to location, whether it's plugged into the cosmic web's hidden currents or stranded in a desert with no way to refuel. What's emerging is a new picture of galactic life cycles, one where the missing baryons are the unsung puppeteers. They dictate how quickly galaxies burn out, how bright they shine, even how they're shaped. And if we've underestimated their role, it means our entire understanding of galaxy evolution might need rewriting not as isolated islands, but as dynamic players in a vast, interconnected system we're only beginning to map. The universe, it seems, keeps its most important players just out of sight, pulling strings from the shadows. To understand why half the universe's baryons went missing, we need to rewind time way back to the universe's first split second of existence. Picture this: a newborn cosmos, smaller than a single atom, suddenly exploding outward faster than light itself. This was cosmic inflation, a fleeting but universe-defining moment when space stretched exponentially, smoothing out wrinkles in reality and laying the groundwork for everything we see today. But inflation didn't just shape the cosmos, it might have flung baryons into hiding like confetti in a hurricane. Here's how it could have happened. During inflation, quantum fluctuations, tiny ripples in the fabric of spacetime, were stretched to cosmic proportions, becoming the seeds for galaxies and galaxy clusters. But those same fluctuations might have also scattered baryonic matter unevenly, leaving some regions denser than others. As the universe expanded and cooled, gravity began gathering matter into the filaments and nodes of the cosmic web we see today. Yet the baryons in the emptier regions, they were stretched so thin, so diffuse, that they slipped between the cracks of detection. It's like shaking a bag of glitter. Most clumps together in obvious piles, but some particles drift so far apart they become nearly invisible. The aftermath of inflation set the stage for another challenge: temperature. The early universe was a searing plasma, so hot that protons and electrons couldn't even bind to form atoms. When things finally cooled enough for atoms to stabilize around 380,000 years after the Big Bang, light could travel freely for the first time, creating the cosmic microwave background we observe today. But that same clarity had a downside. The sudden transparency meant baryons were no longer trapped in a glowing fog. They could hide in the darkness, their faint signals swallowed by the void. What's wild is that inflation's fingerprints might still be visible in the missing baryon problem. The same stretching that smoothed the universe also dispersed matter so efficiently that some baryons never had a chance to clump into galaxies or stars. Instead, they linger in those whisper-thin filaments of the WHIM, their signals diluted by billions of years of expansion. Modern telescopes are essentially hunting for ghost particles so spread out that spotting them requires stitching together clues from across the observable universe. Yet inflation isn't just a culprit, it's also a guide. The very same process that scattered baryons also created the cosmic web's large-scale structure, the highways along which those missing particles eventually drifted. By mapping the web's faint glow, astronomers are reverse engineering inflation's legacy, tracing how those primordial ripples steered ordinary matter into the shadows. And if we're right, the missing baryons aren't lost at all. They're exactly where inflation left them, woven into the fabric of the universe itself, waiting for us to learn how to see them. The Fermi paradox, the eerie silence of the cosmos despite its vast, star-studded expanse, might seem unrelated to missing baryons at first glance, but dig deeper, and these two mysteries could be strands of the same cosmic knot. If half the universe's normal matter is scattered so thinly it's nearly invisible, what does that mean for the development of life? Could the missing baryons be part of why we haven't heard from anyone out there? Consider this. The cosmic web's structure dictates where galaxies form, and galaxies are the cradles of stars, planets, and potentially life. But if baryons are unevenly distributed, piled up in some regions, and vanishingly sparse in others, entire swaths of the universe might be starved of the raw materials needed to build habitable worlds. Imagine a cosmic desert where galaxies are oases, but the distances between them are so vast, and the gas so diluted, that even if life arose, it's isolated beyond hope of contact. The Great Filter, a hypothetical barrier to detectable civilizations, might not be a single event like nuclear war or asteroid impacts. It could be baked into the universe's very architecture, a scarcity of usable matter in just the right places. Then there's energy. The WHIM superheated gas isn't just hiding baryons, it's a dynamic, chaotic environment. For a civilization advanced enough to broadcast signals across interstellar space, the diffuse, turbulent nature of the cosmic web could act like a fog, scattering or absorbing transmissions before they ever reach another galaxy. Even if life is common, the universe's missing baryons might have trapped each civilization in its own bubble, their signals dissipating into the void before they can ever be heard. But here's the twist. What if the opposite is true? Some theorists suggest the missing baryons could be a prerequisite for life. Galactic winds, those violent outflows from stars and black holes, don't just eject gas. They enrich intergalactic space with heavy elements like carbon and oxygen. Without these ejections, the universe might lack the diversity of elements needed for rocky planets or complex chemistry. The same forces that hide baryons could also be seeding the cosmos with life's building blocks, delivering them to future galaxies like cosmic UPS trucks. The unsettling possibility. We might be living in a Goldilocks zone of baryon distribution, a rare pocket where enough matter clumped together to form stars, planets, and us, while the rest was scattered just widely enough to keep the universe quiet. If that's the case, the missing baryons aren't just a physics problem. They're a cosmic curtain drawn across the stage of the universe, leaving us to wonder if we're the only audience, or simply too far from the next act to hear the applause? What if the missing baryons aren't just hiding? What if they've transformed into something entirely unexpected? While the WHIM remains the leading explanation, some scientists have dared to explore wilder possibilities. One provocative theory suggests baryons might decay over cosmic timescales, breaking down into exotic particles we've yet to discover. Imagine a universe where protons, considered stable for all practical purposes, slowly disintegrate over trillions of years, leaving behind a faint drizzle of energy and hypothetical particles like actions or sterile neutrinos. It's a radical idea, but not impossible. Experiments like Super Kamiok and have spent decades watching for proton decay, and while none's been spotted yet, the door isn't fully closed. If even a tiny fraction of baryons decayed since the Big Bang, it could account for a sliver of the missing matter, though far from half. Then there's the primordial black hole hypothesis. Picture the early universe not as a smooth soup of particles, but a bubbling cauldron of ultra-dense knots. Quantum fluctuations during inflation might have compressed some regions so tightly they collapsed directly into black holes no larger than asteroids, some as small as a single proton. These ancient relics, dubbed primordial black holes, could be drifting unseen through space, their collective mass adding up to the missing baryons, the twist. They'd be nearly undetectable unless they happened to pass between us and a distant star, bending its light like a cosmic magnifying glass. While surveys like Unveil have hunted for such microlensing events, the results remain inconclusive. Still, it's a tantalizing thought. What if the universe's lost matter is locked inside countless invisible pinpricks of darkness? Another fringe idea pushes the boundaries of known physics. Baryons might have condensed into strange, ultra-dense objects called quark nuggets. In the chaotic aftermath of the Big Bang, pockets of quark-gluon plasma, the primordial state of matter, could have frozen into bizarre lumps of pure quark matter, shrugging off attempts to detect them with conventional telescopes. These nuggets, if they exist, would be fantastically dense yet cold, lurking in interstellar space like cosmic icebergs. Some researchers even speculate they could explain certain dark matter signatures, though the evidence is thin. The wildest theories challenge our understanding of space-time itself. Could baryons be leaking into extra dimensions, as some string theory models suggest, or trapped in domain walls, cosmic defects in the fabric of reality left over from the universe's violent birth? While these ideas stretch credulity, they highlight a deeper truth. The missing baryon problem forces us to question everything we think we know, yet for all their creativity, these alternatives face a steep hurdle, Occam's razor. The WHIM fingerprints are already in the data, while exotic solutions require new physics with no direct proof. But that's the beauty of cosmology. Sometimes, the most outlandish ideas pave the way for real breakthroughs. After all, dark matter was once a fringe hypothesis too. Until we have the final answer, the universe keeps its options open, daring us to think bigger. And if history's any guide, the truth might be stranger than any theory we've dreamed up so far. Right now, buried in blueprints and testing facilities across the globe, the next generation of cosmic detectives is taking shape. Telescopes so advanced they could turn the faintest whispers of the WHIM into a shout. Leading the charge is the European Space Agency's Athena mission, slated to launch in the 2030s. This isn't just an upgrade, it's a revolution. Athena's X-ray vision will be 50 times sharper than XMM-Newton's, with a field of view 20 times wider than Chandra's. Picture trying to read a restaurant menu from across the street, and then suddenly holding it right under your nose. That's the leap Athena promises. Its instruments, like the X-ray integral field unit, won't just detect the WHIM hot filaments. They'll map their temperatures, motions, and chemical compositions in stunning detail. For the first time, we'll see the cosmic web not as a blurry sketch, but as a high-definition film, revealing how gas flows between galaxies and how those missing baryons shape the universe's largest structures. But Athena won't be alone. NASA's Lynx X-ray Observatory, still in the concept phase, could push the envelope even further. Lynx's mirrors are designed to collect X-rays with nearly perfect efficiency, capturing photons that current telescopes miss. Imagine trying to catch rain with a colander. Lynx would be like using a bucket. Its sensitivity could uncover the WHIM cooler, denser clumps, the ones that slipped through Chandra's net. There's even talk of Lynx spotting missing Lynx filaments so faint they've been theoretical until now. Together, Athena and Lynx could do for the cosmic web what the Hubble Deep Field did for galaxy formation: transform a hazy idea into something tangible, something we can measure and study like never before. And the innovations don't stop there. The upcoming square-kilometer array, a sprawling radio telescope network across 2 continents, will peer into the WHIM slightly cooler regions using hydrogen's faint radio emissions. Meanwhile, the James Webb Space Telescope's successors, like the Habitable Worlds Observatory, might leverage ultraviolet spectroscopy to trace the WHIM faint glow around distant quasars. It's a multi-wavelength assault on the problem, with each telescope bringing its own piece of the puzzle. What's truly exciting isn't just the technology, it's the questions these missions could answer. How much of the WHIM is truly primordial, and how much was ejected by galaxies? Do baryons cycle back into galaxies over cosmic time, or are they lost forever? And perhaps most tantalizing, if we've underestimated the cosmic web's complexity, could there be even more baryons hiding in forms we haven't dreamed of yet? The hunt for missing baryons has always been a game of patience and ingenuity. But with these telescopes on the horizon, we're not just waiting for answers, we're building the tools to demand them. And if history's any guide, every time we've sharpened our vision, the universe has rewarded us with surprises. The WHIM secrets won't stay hidden much longer. While space telescopes like Chandra and XMM-Newton have been workhorses in the hunt for missing baryons, some of the most groundbreaking discoveries are happening right here on Earth, where a new breed of ground-based observatories is turning the cosmic web's faint signals into sharp focus. Take the Atacama Large Millimeter Array, or ALMA, nestled high in Chile's bone-dry desert. Unlike X-ray telescopes that spot superheated gas, ALMA 66 radio antennas specialize in catching the faint millimeter wave glow of slightly cooler filaments, the ones just warm enough to reveal their presence through subtle spectral fingerprints. It's like swapping a flashlight for a heat-sensitive camera, uncovering strands of the cosmic web previously too chilly to notice. Then there's the Dark Energy Spectroscopic Instrument, or DESI, mounted on a telescope in Arizona. DESI isn't just looking for baryons, it's mapping the universe's expansion by measuring the precise distances to millions of galaxies. But here's the genius part. As light from those galaxies travels through the cosmic web, the WHIM filaments imprint their presence by distorting specific spectral lines. By analyzing thousands of these distortions, DESI can triangulate where the missing baryons are hiding, like tracing the outline of a shadow. What makes these ground-based tools so powerful? Sheer scale. Space telescopes are limited by the size of the rockets that launch them, but Earth's observatories can sprawl across mountains and deserts. The upcoming extremely large telescope, with a mirror nearly 40 meters across, will have such sharp vision it could spot individual Baryon filaments around distant quasars, something even Athena won't achieve. And let's not forget the square-kilometer array, a radio telescope network so vast it'll span 2 continents, stitching together a real-time map of the cosmic web's structure with unprecedented precision. The real magic happens when space and ground telescopes team up. X-ray satellites pinpoint the hottest gas, while radio arrays like ALMA trace the cooler strands. Optical telescopes measure how the WHIM bends light, and supercomputers synthesize all this data into a cohesive picture. It's the ultimate cosmic collaboration, a global effort to solve a universal mystery. And as these tools grow more sophisticated, one thing becomes clear: the missing Baryons aren't just hiding, they're waiting for us to learn all their secrets. Magnetism might not be the first thing that comes to mind when you think of the vast emptiness between galaxies, but it could be the silent puppeteer shaping where those missing Baryons hide. Picture this: the same invisible force that guides compass needles on Earth also weaves through intergalactic space threads of magnetic energy stretching millions of light years, twisting and bending the paths of charged particles like an unseen hand redirecting a river. These fields aren't just cosmic decorations, they're powerful enough to steer the WHIM superheated gas, clumping it into denser strands or scattering it further into the void. Take galaxy clusters, for example. These colossal structures are often wrapped in magnetic fields stronger than anything in our solar system, generated by the churning motion of gas and the explosive energy of black holes. When galactic winds blast baryons outward, those particles don't just drift aimlessly. They ride magnetic field lines like commuters on a subway, funneled into specific routes that might explain why some filaments of the cosmic web glow brighter in X-rays, while others fade into near invisibility. It's a cosmic sorting system, one that could be hiding baryons in plain sight by dictating where they pool and where they thin out. But here's where it gets stranger. Magnetic fields don't just organize matter, they can also heat it. When charged particles spiral along these invisible lines, they emit radiation, further energizing the WHIM already scorching plasma. This extra heat might prevent gas from cooling enough to collapse into new galaxies, essentially pressing pause on star formation in certain regions of the universe. Imagine a pot of water that never boils because someone keeps turning up the heat. Magnetic fields could be doing the same thing to intergalactic gas, locking baryons into a state too hot and diffuse to ever coalesce into something we can see. The real challenge: measuring these fields. Unlike gas, magnetism leaves no direct light signature. Astronomers have to get creative, studying how charged particles bend the light of distant quasars, or searching for faint radio waves emitted by electrons spiraling in magnetic fields. Recent observations of polarized light, where waves vibrate in a preferred direction, hint at magnetic structures spanning entire galaxy clusters, but the finer details remain murky. It's like trying to map a city's power grid by watching how streetlights flicker from miles away. And then there's the chicken and egg puzzle. Did magnetic fields shape the cosmic web, or did the web's structure generate the fields? Some theories suggest these forces grew from tiny, seed fields in the early universe, amplified over eons by the motion of gas and dark matter. Others propose they were forged in the violent hearts of the first galaxies, then blown outward by supernova and quasar jets. Either way, the implications are staggering. If magnetic fields control how baryons move, then solving the missing matter mystery might require rewriting not just our maps of the cosmos, but our understanding of the forces that silently govern it. What's clear is this: magnetism adds a wild card to the hunt for missing baryons. It's not enough to know where the gas is. We need to know how invisible fields are nudging it, hiding it, or even heating it beyond recognition. And if we've underestimated their role, it means the universe's ledger isn't just missing entries. It's written in a code we're only beginning to decipher. One thing's for sure: the cosmos never loses its knack for throwing us curveballs. Just when we think we've got the rules figured out, magnetism steps in to remind us there's always another layer to the story. Long before galaxies even existed, the universe was a roiling sea of plasma, so dense that light couldn't travel more than a hair's breadth before bouncing off another particle. In that primordial chaos, something extraordinary happened. Sound waves, not the kind you hear, but massive pressure waves rippling through the hot soup of protons and electrons, like vibrations ringing through a cosmic bell. These weren't just random noise, they were the universe's first rhythm, a pulse set in motion by the competing forces of gravity pulling matter together and radiation pressure pushing it apart. And though the music faded billions of years ago, its echoes still linger today, etched into the cosmos as baryon acoustic oscillations, ghostly fingerprints that help us trace where the missing baryons have been hiding. Here's how it works. Imagine dropping a pebble into a pond. The ripples spread outward in perfect rings, freezing in place the moment the water turns to ice. That's essentially what happened in the early universe. Those primordial sound waves traveled outward until the cosmos cooled enough for atoms to form, around 380,000 years after the Big Bang. At that moment, the waves froze mid-ripple, leaving behind spherical shells of slightly denser matter, like cosmic Russian nesting dolls, with galaxies more likely to form on their surfaces. The distance between these shells, roughly 500 million light-years, a measurement so precise it's become one of cosmology's most reliable yardsticks. But here's where it gets clever. By mapping where galaxies cluster today, seeing how often they're separated by that 500 million light-year scale, astronomers can reverse engineer where baryons must have been. Think of it like finding footprints in wet cement. Even if the culprit is long gone, the impressions reveal where they stood. Surveys like the Sloan Digital Sky Survey have used this technique to create three-dimensional maps of the universe, revealing a vast foam-like structure where galaxies align along the crests of those ancient waves. And since baryons were the original material those waves traveled through, their distribution today should still reflect those patterns, meaning the missing ones aren't truly lost. They're simply part of the cosmic fabric, woven into the same large-scale structure we can already see. There's a twist, though. While baryon acoustic oscillations confirm that baryons were evenly spread in the early universe, they don't fully explain why half seem to vanish when we tally up modern observations. That's where the WHIM comes back into play. The oscillations tell us where to look, those vast, faint filaments between galaxy clusters, but not how the baryons became so diffused. It's like knowing a forest exists but needing infrared goggles to spot the animals hidden beneath its canopy. What makes these oscillations so powerful is their neutrality. Unlike other methods that rely on detecting light or heat, baryon acoustic oscillations are a statistical tool, unbothered by whether matter is hot, cold, glowing, or dark. They're the universe's own paperwork, a ledger stamped in the moments after creation. And as telescopes grow more advanced, these frozen ripples may yet reveal even deeper secrets, like whether the missing baryons are truly missing, or whether we've just been reading the cosmic map with the wrong key. One thing's certain, in the hunt for the universe's hidden matter, sometimes the loudest clues come from the echoes of silence. Galaxy clusters, those bustling metropolises of the cosmos, aren't just collections of stars and dark matter. They're also shrouded in colossal veils of gas, so vast they could swallow entire galaxies whole. These intergalactic gas clouds, some stretching millions of light years, were long overlooked because they don't shine like stars or glow as vividly as nebulae. But recently, astronomers have peeled back the curtain on these invisible giants, revealing them as potential hiding spots for at least some of the universe's missing baryons. Take the Perseus cluster, for example. This massive gathering of galaxies, located about 240 million light-years away, is swaddled in a fog of superheated gas that emits faint X-rays. At first glance, the gas appears too hot and thin to account for much missing matter until you realize just how much of it there is. The cloud enveloping Perseus weighs as much as trillions of suns, a staggering reservoir of baryons floating between galaxies like an ocean between islands. Similar clouds have been spotted around other clusters, each one a trove of hidden matter previously written off as empty space. What's fascinating is how these clouds form. When galaxies collide within clusters, a common occurrence in these crowded cosmic neighborhoods, they don't just trade stars. They also strip gas from one another through a process called ram pressure. Picture two cars driving through a heavy downpour. The faster they go, the more water gets pushed aside. In galaxy collisions, the rain is intergalactic gas, and the windshield is the gravitational pull of the cluster itself. Over time, this stripped gas accumulates, pooling into diffuse clouds so immense they blur the line between galaxy and void. But here's the catch. These clouds are so hot, often reaching tens of millions of degrees, that their atoms are ionized, meaning they've lost their electrons. In this state, they don't absorb or emit much visible light, making them nearly transparent to traditional telescopes. Only X-ray observatories can spot their faint glow, and even then, it takes painstaking analysis to separate their signal from the background buzz of the universe. The real breakthrough came when scientists realized these clouds might not stay hot forever. Some models suggest that as the gas slowly cools over billions of years, it could condense into new stars or even fuel quasars at the hearts of galaxies. If true, these clouds aren't just passive reservoirs, they're cosmic batteries, storing baryons until gravity taps them for future use. That would mean the missing matter isn't lost, it's just stuck in transit, waiting for the universe to press play. Yet mysteries remain. Why do some clusters have enormous gas clouds, while others seem starved? Could magnetic fields or dark matter be shaping how these reservoirs form? And most tantalizing of all, if we've underestimated the role of these clouds, could they be hiding even more baryons than we've accounted for? The answers might lie in the next generation of telescopes, which will peer deeper into these ghostly structures than ever before. What's clear is this: the universe doesn't lose matter. It just gets creative about where it puts it. The cosmic microwave background is like the universe's baby picture, a faint glow from when everything was just 380,000 years old. This afterglow of the Big Bang carries an incredible secret, an imprint of how much normal matter, how many baryons, existed at the dawn of time. Think of it as a cosmic ledger, frozen in microwaves, recording the exact balance of particles in those first moments. When scientists measured this snapshot with missions like Planck and WMAP, they found something extraordinary. The universe's baryon density was precisely 5% of its total mass energy. number so exact it might as well be written in celestial ink. That measurement became the gold standard for cosmic accounting. It told us how much stuff we should be finding today. The problem, when we add up all the visible matter, stars, galaxies, gas clouds, we come up short by nearly half. The cosmic microwave background isn't just a relic, it's a detective's first clue. Those microwaves reveal not only the total Baryon count, but also how they were distributed like a fingerprint left on the universe's surface. Tiny fluctuations in the CMB's temperature, variations of just 1 part in 100,000, show where matter was slightly denser or sparser in the infant cosmos. These ripples became the seeds for everything we see today: galaxies forming in the denser spots, voids stretching between them. But here's the brilliant part. Those same fluctuations let us predict where the missing baryons should be now. The patterns in the CMB act like a cosmic blueprint, showing how gravity would have sculpted matter over billions of years. Simulations based on this blueprint trace 2 possible fates for baryons. Either they collapsed into galaxies and clusters, or they were swept into the vast intergalactic web. When observations didn't match the first scenario, scientists knew exactly where to look next. The cosmic microwave background didn't just highlight the missing matter, it pointed to the voids between galaxies as the most likely hiding place. And the plot thickens. The CMB also carries subtle distortions caused by later interactions with matter, clues about where baryons went after the universe's infancy. One example, the Sunyaev-Zeldovich effect. When CMB photons pass through galaxy clusters, they get a tiny energy boost from hot electrons in the surrounding gas, leaving a distinct fingerprint. By mapping these distortions, astronomers have weighed the baryons in clusters, confirming that even these massive structures don't hold enough to balance the cosmic books. That leaves the intergalactic medium the only place left where baryons could match the CMB's original accounting. The cosmic microwave background is more than a relic. It's the universe's way of holding up a mirror. By comparing its pristine record of the past with today's imperfect surveys, we're not just hunting for missing matter. We're piecing together the story of how the cosmos grew up and realizing just how much of that story is still written in invisible ink. The hunt for missing baryons isn't just a scientific challenge, it's a global mission, uniting astronomers across continents in a race to map the invisible. Picture this: teams from Japan to Chile, from South Africa to Norway, all training their telescopes on the same cosmic voids, sharing data in real time, stitching together a map of the universe's hidden highways. This isn't just collaboration, it's a testament to how big science operates in the 21st century, where no single telescope, no lone genius, can crack the cosmos alone. Take the eROSITA project, a German-Russian X-ray telescope designed to scan the entire sky with unprecedented sensitivity. Launched in 2019, it's already uncovered vast reservoirs of hot gas in galaxy clusters, revealing how baryons might be funneled along the cosmic web's filaments. But eROSITA doesn't work in isolation. Its data is cross-referenced with optical surveys like the Dark Energy Survey in Chile and radio observations from India's giant meterwave telescope, creating a multi-wavelength tapestry that no single instrument could weave alone. Then there's the Illustris-TNG collaboration, an international supercomputer effort simulating billions of years of cosmic evolution. Researchers from Harvard to Heidelberg feed their observations into these models, testing theories about where baryons might be hiding and predicting where telescopes should look next. It's a feedback loop between simulation and observation, with each discovery refining the next. But perhaps the most ambitious effort is the upcoming Athena mission, a European-led X-ray observatory set to launch in the 2030s. With contributions from over 100 institutes across 21 countries, Athena's goal is nothing less than a full census of the universe's hot gas, a project so vast it requires the combined expertise of astrophysicists, engineers, and data scientists from every corner of the globe. What's striking is how these projects transcend borders, both literally and figuratively. In an era of division, the missing Baryon problem has become a rare unifying force, reminding us that the cosmos doesn't belong to any one nation. The answers are out there, written in X-rays and ultraviolet light, waiting for humanity working together to read them. And if history's any guide, the next breakthrough won't come from a single a moment, but from the collective patience and ingenuity of thousands, all peering into the dark, determined to solve one of the universe's oldest tricks. You don't need a PhD or $1 million telescope to join the hunt for missing baryons. Some of the most exciting discoveries start with everyday people like you. Citizen science projects have become a game-changer in astronomy, turning curious observers into real contributors to cutting-edge research. Platforms like Zooniverse host initiatives where anyone can sift through telescope data, flagging unusual patterns or faint signals that might lead professionals to hidden baryon reservoirs. Imagine scrolling through images of galaxy clusters on your lunch break and spotting a wisp of gas everyone else missed. Your name could end up in a scientific paper. One standout project is Galaxy Zoo, where volunteers classify galaxies to help researchers map the cosmic web's structure. By identifying galaxy shapes and orientations, you're indirectly tracing the gravitational scaffolding that channels baryons into filaments. There's also Radio Galaxy Zoo, which lets you pinpoint jets of plasma spewed by supermassive black holes, clues to how galactic winds scatter baryons into the void. These projects aren't just busywork. They've led to actual discoveries, like rare green pea galaxies that might hold secrets about intergalactic gas flows. If you're more into data crunching, Einstein at Home harnesses your computer's idle processing power to analyze signals from X-ray telescopes, searching for the faint fingerprints of the WHIM. It's like running a cosmic screensaver that could help solve a billion-year-old mystery. Even stargazing apps like Universe 2 Go let you contribute observations of deep sky objects, adding to databases that researchers use to track baryon-rich regions. The best part? You don't need expertise to start. Many projects include tutorials, and the science teams often host live Q and as to explain how your work fits into the bigger picture. Every click, classification, or observation gets us closer to balancing the universe's ledger. So why not dive in? The next missing piece of the cosmic puzzle might be hiding in the data, waiting for you to find it. For those who prefer hands-on learning, local astronomy clubs often collaborate with universities on outreach programs. Events like Globe at Night measure light pollution, but also train participants to recognize subtle gas clouds in telescope images. Who knows, your backyard observations might reveal a filament of the cosmic web nobody noticed before. The universe's secrets aren't just for professionals anymore. They are for anyone willing to look up and wonder. Solving the missing baryon puzzle wouldn't just fill in a cosmic ledger. It could rewrite the rules of physics itself. Think of it like uncovering a hidden chapter in the universe's instruction manual, one that forces us to rethink everything from galaxy formation to the very nature of matter. Take gravity, for example. Our models of how galaxies evolve rely on precise calculations of baryonic matter's gravitational pull. If half of it has been hiding in plain sight, we might need to recalibrate how we simulate cosmic evolution, tweaking the delicate balance between dark matter's scaffolding and ordinary matter's weight. Then there's plasma physics, the study of superheated, ionized gases like the WHIM. Most of our understanding comes from labs or solar winds, but the WHIM extreme conditions push the boundaries of known behavior. Its gas is so thin, it defies earthly analogs. At just 1 atom per cubic meter, it's 1,000,000 times sparser than the best vacuums we can create on Earth, yet hotter than the sun's corona. Discovering how this plasma behaves could unlock new principles of electromagnetism and thermodynamics, even influencing fusion research or advanced propulsion concepts. But the implications stretch even further. The WHIM existence hints at undiscovered physics in the early universe. Inflation, the faster-than-light expansion after the Big Bang, should have distributed baryons uniformly. Yet the cosmic web's filaments show intricate clustering, suggesting forces beyond gravity shaped their fate. Could primordial magnetic fields, born in the universe's first seconds, have steered baryons into these threads? Or do we need entirely new particles or interactions to explain their distribution? The biggest twist might be cosmological parameters, the universe's expansion rate, dark energy strength, even the mass of neutrinos. All are calculated assuming we know the total baryon density. If half were missing, those numbers might need adjustments, potentially resolving tensions like the infamous Hubble constant crisis, where different methods give conflicting expansion rates. And let's not forget the philosophical shift. Finding the missing baryons proves how much of reality exists just beyond our perception, waiting for the right tools to reveal it. If we've overlooked something as fundamental as half the normal matter, what else might be hiding in the cosmos' shadows? Each answer doesn't just close a gap, it opens a door, reminding us that the universe is always more subtle, more inventive than we dare assume. So where does this leave us in the grand cosmic detective story? We've chased invisible threads across billions of light years, peeled back layers of the universe we once thought were empty, and found half the missing matter hiding in plain sight, superheated gas so diffuse it's like mist on a mirror. The discovery of the WHIM isn't just about balancing some celestial spreadsheet. It's a revelation that the universe's most important structures might be the ones we can barely see. These filaments aren't just hiding baryons, they're the scaffolding of reality, the unseen currents shaping galaxies, fueling star birth, and perhaps even guiding the evolution of everything we call home. But the deeper lesson here is humility. For decades, we assumed the voids between galaxies were barren, only to realize they're bustling with energy and movement. It's a reminder that the cosmos specializes in hiding its secrets in the last places we'd think to look. If something as fundamental as half the universe's normal matter could evade detection until the 21st century, what does that say about the limits of our perception? The WHIM forces us to confront an unsettling truth. We're still beginners in understanding the universe, piecing together clues with tools that might seem laughably crude to future civilizations. And yet, every answer breeds new questions. If baryons can vanish into the cosmic web's faint glow, could dark matter be hiding in an even more elusive form? Are there phases of matter or energy we haven't even imagined yet, woven into the fabric of space-time itself? The hunt for missing baryons has shown us that the universe is far stranger, far more inventive than our textbooks ever suggested. So here's the real kicker. If we've only just begun to see the hidden architecture of everything, what else is out there waiting for us to invent the tools, the theories, the imagination to uncover it? The cosmos has spent 13.8 billion years practicing its sleight of hand. The question isn't whether it has more tricks up its sleeve, it's how many will be lucky enough to unravel next.